For the second half of section 2.1, we're going to talk about the area problem. The area problem addresses this issue that maybe at times we want to find an area that doesn't fit a nice geometric pattern. For example, we know how to easily find the area of a rectangle. We just do length times width. We know area for a triangle. It's 1/2 base times height. Maybe area for a circle. It's 2 pi. Nope, just kidding. That was circumference. It's pi r squared. So if we have a nice, neat geometric figure, we can calculate the area using one of the already discovered area formulas. However, taking a look at this graph that we have for a function f of x, that's our blue curve, maybe we want to find the area underneath that curve, above the x-axis, and between two bounds. So we have our bound on the left, which is x equals a, and then our bound on the right, where x equals b. So we're looking at this entire shaded region. That doesn't fit a perfect geometric shape, but we still might want to know what the area of that is. And there's a number of different reasons why this would be important. The first one that comes to mind is calculating probabilities, but at this point, let's just imagine that we know the application, we want to know how to find that area. There's not a way to do that without it being a nice, neat geometric shape. So calculus came in and said, we're going to figure this out. Now that we understand what limits are, we can push things to the limit. We're going to push math to the limit to create calculus. And basically the solution was, we're going to create a bunch of rectangles. So on the right side of the screen, I've created a function, the blue curve. We'll call that f of x. And I've also put up my left and right bounds with red lines. So that's kind of like the a and the b. What we're going to do to find the area is we're going to start off with an approximation, and we're going to approximate the area in a very rudimentary way. We're going to draw shapes that we already recognize, shapes that we already know how to find area of, like rectangles. So we'll create a partition along the x-axis. So you see these 3 green tick marks. I've divided my x-axis up into 4 parts, and then I'm going to plug the x values for each of the endpoints into my function to generate these green dots on the function. Then I'm going to use those green dots to create rectangles. So the bottom of the rectangle is on the x-axis, and then the sides of the rectangle are made by the function output at the end of our partition pieces. And then we just calculate area 4 different times and then add it up. So we'll calculate the area for our first rectangle, finding some length and some width to multiply. Then we'll do it again for the second rectangle, calculate that. Third rectangle, calculate that, and fourth rectangle. So we'll add up 4 separate areas as a way to approximate the total area. Now again, just like the last problem that we looked at, this is an approximation that doesn't look that impressive. However, the smaller and smaller we make our partitions, I'm going to call that a delta x, so the smaller we make this, the better the approximation gets. So let's go back to our first drawing and kind of take a look at that. Maybe instead of 4 rectangles, I create 10. So let's draw 1, 2, 3, 4, 5, 6, 7. Oops, that would give me 11, 12. Okay, let's say we have 12 rectangles because that's how my spacing worked out. But notice that if I draw 12 rectangles underneath my curve, Yes, some of them are going to go outside of the area that we want. However, the little areas that are reaching outside of our shaded region are smaller overall than they would be if we used really large rectangles. So this is going to take a while to draw it, but let me just finish it off. So I've drawn all of my rectangles. Each of the rectangles, the upper right corner, falls perfectly on my curve. So that's how I was deciding how tall each rectangle needs to be. Some of these went outside as an extra, overestimating the area. Some of these were too short, like an underestimate of the area. But notice that the pieces that are outside of the shaded region that we do want the area for, they're so much smaller than they were in the picture with just 4 rectangles. So this area is a much worse estimation, especially take a look at this one. So here the overestimate is so large. The smaller and smaller we make those rectangles, the better and better our approximation will be. And so in this case, the limit is being applied to making delta x very small. We'll write something like the limit as delta x goes to 0, for example. And then we would be able to add up all of the areas of those rectangles that are infinitely thin, and we can calculate the area underneath the curve above the x-axis between two boundaries like A and B on the left and the right. Now, you can draw your rectangles in different ways, so we're going to look at how to estimate an area using rectangles. And we're going to look at the same function, but we're going to calculate our areas in 2 different ways. So let's start by looking at the function on the left, or the graph rather. So this function is the x squared plus 1 function. And the rectangles that are drawn for us start at x equals 0. They increase as x goes up by 1. And then the final edge of the rectangles that are drawn stop at x equals 3. So we're going from 0 to 3. We want to estimate this area using 3 rectangles. So we need to calculate the area for each one of these rectangles. Notice that the top left corner of each rectangle lives on the function. We call this the left endpoint. So we're using the left endpoint to create these rectangles. And now we just need to go through and create the 3 different areas. So let's call this area 1, area 2, and area 3. So for area 1, we need our width of the rectangle, and we need the height, so that we can multiply those together to calculate the area. The rectangle is exactly 1 unit wide, and the rectangle is 1 unit tall. So we have 1 times 1 for an area of 1 square units. Then we move on to the second rectangle. This rectangle is also 1 unit wide, but this one is actually 2 units tall. So the area of that second rectangle is 2 units squared. And we have a third rectangle to calculate. This one happens to have the same width, 1 unit wide. But this one's actually 1, 2, 3, 4, 5 units tall. So we have 5 square units for the third rectangle. And then to find our total approximate area, we just add the area of all 3 rectangles. So we have 1 plus 2 plus 5, which is 8 square units. Now this is one approximation for the area. Remember, approximations are not exact answers, so this is off by a little bit. Looking at our picture, we can see that underneath the curve, our first rectangle missed this much space. Our second rectangle missed this much space. And our third rectangle missed this much space. So this is a really bad underestimate, right? All of that red space is pretty large, so we can tell that this number is too small to be the correct answer, but at least it's a start, right? You got to start somewhere. Now in comparison, let's take a look at the picture on the right. Same function. We're still looking at the area between x equals 2 and x equals 3, but these rectangles are drawn so that the top right corner is on the function. We call this the right endpoint. It's the right endpoint of each rectangle that is on the function, determining exactly how tall these rectangles should be. We still have 3 rectangles, so I'm going to label them 1, 2, and 3, and we'll calculate the area the same way we did with the last one. So the first rectangle is 1 unit wide, 2 units tall, so that's going to look like 1 times 2 for 2 square units. The second rectangle, also 1 unit wide, but this one's actually 1, 2, 3, 4, 5 units tall. So we have 5 square units for the second rectangle, and then we have our third rectangle. Still 1 unit wide, but this one is 1, 2, 3, 4, 5, 6, 7, 8, 9 units tall. So we have 9 square units for the third rectangle. And then to find our total approximate area, we add all of these together. 2 plus 5 plus 9, we get 16 square units. Now, just like the last one that we just calculated, this is not an exact answer, it's an approximation. But this approximation is an over-approximation. Notice that each one of these rectangles goes beyond the curve, and we only wanted the area under the curve. So we know that this is going to be an over-approximation. So using the left endpoint, we got an under-approximation. Using the right endpoint, we got an over-approximation. And that's not always how it works. It just so happens to be that way because the function is an increasing function. We'll learn more about that later. But I just wanted to show you how we start off with drawing these rectangles to approximate the areas so that we can start to answer the question of what is the area of this non-geometric shape. Now, if we had drawn skinnier rectangles, the approximations would be closer and closer to exact, and that's what we're going to learn about in the second half of this semester.